The $10 billion James Webb Space Telescope is NASA's largest and most powerful space science telescope, which will probe the cosmos to uncover the history of the universe from the Big Bang to the alien planet formation and beyond. Its greatly improved infrared resolution and sensitivity will allow it to view objects too old, distant, and faint for the Hubble Space Telescope. Welcome back to Cosmos Observer. Let's look at the eyes of the cosmos as it enters its final ordeal. Scientists are overwhelmed by the results so far and are currently looking forward to the final phase of Webb's commissioning. The final phase of commissioning requires the calibration, confirmation, and stress testing of the remaining instruments on board. It took 30 days for the James Webb Space Telescope to travel nearly 1 million miles to its permanent home, a Lagrange point. Let's look at some of the main instruments involved in this telescope. The first one is the near-infrared camera. It is an infrared camera which performs two main tasks. Firstly, as an imager from 0.6 to 5 micron wavelength, and secondly, as a wavefront sensor to keep the 18-section mirrors functioning as one. It is also used to provide information to align the 18 segments of the primary mirror. Utilizing the data transmitted by NURCAM, scientists were able to get the correct angle of all the mirrors on board. It is designed to operate at 37 Kelvin, minus 400 degrees Fahrenheit, so it can detect infrared radiation at this wavelength. NURCAM's 4 major goals include 1. To study the physical and chemical conditions of objects in our solar system with the aim of understanding the origin of the constituent elements of life on Earth. 2. Explore the formation and evolution of the first luminous objects and reveal the reionization history of the universe. 3. To determine how the objects seen today, galaxies, active galaxies, and clusters of galaxies, have come together and evolved from gases, stars, and metals found in the early universe. 4. To improve our knowledge of the birth of stars and planetary systems. Next up is the fine guidance sensor and near-infrared imager and slitless spectrograph. It comprises a fine guidance sensor and a science instrument, a near-infrared imager and spectrograph. The FGS NIRS was designed by the Canadian Space Agency and built by Honeywell. It looks at the light from the wavelengths of 0.8 to 5 microns. NURS is an independent space instrument. Spectroscopy mode is capable of performing exoplanet spectroscopy. FGS helps in providing data to the JWST attitude control system, and in order to achieve this, it has a big sky coverage and sensitivity. While taking a picture per second, the FGS keeps the observatory on track and pointing towards the right segments of space. This is a very vital and precise job that cannot be overlooked. The next instrument is the mid-infrared instrument. MIRI requires both a repositioning of the Webb as well as a boost from a cryocooler in order to get to its ideal chilly resting spot. MIRI can see wavelengths that are longer than our eyes can see, whereas most of the other instruments on Webb can see from the start of the near-infrared or even the shortest orange visible light. MIRI utilizes arsenic-doped silicon arrays for observations at these wavelengths. Lastly, the near-infrared spectrograph, which is the powerhouse of the invention. The NURS Spec instrument is a multi-object spectrograph and is capable of simultaneously measuring the near-infrared spectrum of up to 100 objects, like stars or galaxies, with low, medium, and high spectral resolutions. Thanks to its unique micro-shutter array, which helps in controlling the aperture with precision. Cold space radiators on the JWST Integrated Science Instrument Module, passively the NURS Spec instrument, which operates at minus 235 degrees Celsius. NURS Spec consists of 2 electro-optical systems, which are calibration assembly, bearing 11 light sources and 1 integration sphere for the internal spectral and flat field calibration of the instrument. Focal plane assembly contains the focal plane composed of 2 sensor chips. NURS Spec also includes 4 mechanisms, which are filter wheel assembly, 8 positions with 4 long-pass filters for science, 2 broadband filters for target scanning, 1 closed and 1 open position. Refocus mechanism assembly, equipped with 2 mirrors to refocus instruments. Micro shutter assembly, for multi-object spectroscopy and static slots and IFU aperture. Grating wheel assembly, 8 positions bearing 6 gratings, a prism for science, and a mirror for target acquisition. With all the time, energy, and money spent on the project, You would think it is important that everything works optimally, but the truth is, that part of the web is already shattered. This highly regarded instrument has always presented NURCAM with a faulty photo as part of the JWST alignment process. Throughout the image, there were sections that were blackened and missing. What's more stunning is that this wasn't an oversight. NASA scientists were aware of the 14% that were defective, but instead of changing them and risking harm to other lenses, they sealed off the non-working rows and continued to operate the camera. The black streaks shown across the NURS Spec photo are the result of this decision, although NASA is okay with it. NASA deserves credit for embracing imperfections. The JWST is currently undergoing its thermal stability test. The purpose of this challenge is for the telescope to withstand the modifications and demonstrate that it can perform at its best regardless of the circumstances. It will be monitored and subjected to various degrees of sunshine, causing the observatory to fluctuate in temperature. NASA scientists will examine the observatory's instruments closely to assess their performance, calibration, and general operations. Because these instruments are one of a kind and each was hand-picked, the stakes are quite high. The Webb telescope will begin the thermal stability test by adopting a scorching attitude of around 0 degrees pitch for 5 days, dripping with astronomical sweat. NASA's scientific team will put the sensors through a battery of experiments to replicate conceivable conditions in severe settings, including heating and thermal stabilization. After the heat, the telescope will be immersed in freezing temperatures above 45 degrees of the pitch from the sun for another week. Once stabilized, it will turn -5 degrees towards the sun and heat back. The instruments will be constantly checked at both attitudes and throughout the transition. The team will use the telescope instruments to learn more about how they work at each extreme and in the middle. Because some of the equipment was designed to function best at specific temperatures, it's clear that acclimating the observatory to all extremes is critical. The telescope and instruments used to study the infrared universe must be cool. As a result, scientists want to know how it works at greater temperatures. The point spread function or sharpness of the images communicated to the scientists will also be measured by NASA. The main mirror has already been calibrated for clear views, but each instrument has sub-abilities. Filters that capture color information and diffraction graphs that slice incoming light into its right color group are 2 examples of such abilities. All of these abilities must be evaluated to establish a formal baseline. Even multi-billion-dollar space missions undergo routine quality assurance reviews. Only 2 months remain until the JWST is completely operational and ready to peer into the heart of the cosmos, but there are still many tests to be completed. What do you think about JWST's chances in this challenge? Please share your expectations on JWST in the comments section below.